Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're going to be taking a look at this Tandy Radio Shack RGB monitor. It's the Tandy CM-1. And I can hear a collective groan right now because it's another monitor video on Adrian's Digital Basement. But I think that this one's kind of interesting, and I don't think anyone's ever done any videos about this particular monitor before. While this monitor might look just like a standard Tandy monitor, which there were a whole bunch, this one was actually designed for use with the Tandy 2000. That was their upgrade to the Tandy 1000 line that was aimed more squarely at the business market, with higher resolution graphics and sound over the Tandy 1000 line, and consequently it required its own dedicated monitor, hence the CM1 here. The lack of true PC compatibility was a bit of a death knell for the Tandy 2000 line, and it was quickly replaced with subsequent machines that were fully MS-DOS compatible, but also those machines adopted a more standard CGA and EGA video outputs format, which of course the CM1 monitor here and the original Tandy 2000 was not using. And that's because the Tandy 2000 had a proprietary 26 kilohertz video signal that offered 640 by 400 resolution, which was a nice upgrade over the 15 kilohertz NTSC derived CGA format used on everything else that only offered 200 lines of resolution. That means if you tried to plug this monitor into any other Tandy computer or even a regular PC, it was not going to work. That was, of course, unless you had a special video card like this STB Super Res 400, which I repaired on the last video, that promises to bring compatibility for monitors just like this to regular PCs. So in this video, I want to take a look at this monitor close up, take it apart, make sure there's nothing that looks obviously wrong with it, and if it's all good, hook it up to this STB video card here and see if we can see that glorious 640 by 400 resolution running on this old monitor. So without further ado, let's get right to it. So the Tandy CM1, or Color Monitor 1. You may notice looking at this that the phosphor has a distinctive blue-green appearance to it, and that's a telltale sign that Mitsubishi was the manufacturer of the picture tube, and most likely the entire rest of this monitor. Looking closely at the front of the monitor, we have the badge, we have a power switch, and there's actually a little flip-down door right here, and it's a little difficult to show, but there are two knobs right here for brightness and contrast. On the back, we have a fixed power cord, which is sort of something I really hate. And then we have an EIJ-8, I think is the connector type. This is a Japanese style digital TTL connector, although it can be used for other types of inputs as well, like composite video and stuff like that. And then we have 4 holes right here for some kind of adjustment of controls on the inside of the set, although there's room for a sticker here, nothing is actually labeled. There's a serial number on this monitor, RS129708. And then we have the Tandy Radio Shack sticker. It's the RGB high resolution monitor CM1, 120 volts, 60 hertz, and the model number is 26-5112, made in Japan, and there's the FCC ID. Now, if you're wondering about this 640 by 400 video standard that this monitor adheres to, you may be wondering why you've never even heard of it. Well, it actually originated in 1982 in Japan from the NEC PC9801 series of computers. In order to display a full screen of Japanese characters, the regular 640 by 200 that was available for CGA was just not good enough. And I think the idea was with NEC is that using the higher resolution, you'd be able to have much more clearly defined glyphs that would allow the display of the text in a very clear and readable fashion. And of course, when you're displaying Roman characters as well, that higher resolution also results in a much sharper, easier to read text, which was really one of the benefits of why MDA, or the monochrome standard that came out with the original IBM PC, had higher resolution fonts, is because that ran at a resolution of 640 by 350 lines versus just the 200 lines of CGA. So because in Japan they were already selling machines using this standard, it made sense for IBM to adopt that same high resolution video standard, and then they could just import one of the Japanese monitors like this one and OEM brand it with the Tandy Radio Shack, and then there you go. You have the Tandy CM1. A little bit of Googling has resulted in me finding the original service manual for this monitor, which is fantastic. We should be able to learn a little bit about its technical specifications because I can't really find any other info. And if there are any faults with this monitor, we should be able to troubleshoot it by using the schematics that are included in here. So right off the bat, we can tell here that this is an RGB TTL monitor, which we already knew really because that STB card that works with this monitor outputs a TTL RGB signal. It does support 15 colors, so it does support using the intensity bit for those bright colors, kind of like the CGA standard, although I wouldn't be surprised if this monitor does not support CGA brown, because this is derived from the Japanese standard, which means it has 2 shades of yellow, light yellow and dark yellow. The high voltage on this monitor runs at 22.5 kilovolts, very typical for 13-inch monitors. I'd say that's pretty standard. Whoever wrote this service manual includes a nice theory of operation, which is actually quite comprehensive and really well written when it comes to how all the different subsections of the monitor work. Section 7 is talking about the high voltage hold down circuit. This is designed for safety. In case something goes wrong in the monitor and you end up with like 35 kilovolts, that actually can start to produce X-rays. So some circuitry here on the monitor monitors the voltage coming out of the flyback transformer by using an extra winding. And in case it ever goes over a set threshold, will actually shut down the high voltage. And actually what it does here is it stops the horizontal oscillator, which means it will kill the high voltage. Here are the colors this monitor supports. As I mentioned, it has dark yellow and yellow. It does not have brown, which is typically what the dark yellow is here, where IBM designed CGA to add a little bit of extra red component to the dark yellow that produced the brown. What we can be pretty sure of here is that this monitor supports only one horizontal scan rate and is 26.4 kilohertz. That means this monitor absolutely positively will not work hooked up to a CGA video card. Sometimes you can get away with a couple kilohertz difference and you can adjust the horizontal hold control to get it to lock in, but we're talking 15.7 kilohertz for CGA all the way up to 26. That is far too much of a deviation for this monitor to actually work. Otherwise, overall, I'm really impressed with this manual. It has a lot of information on how to calibrate the monitor, get it adjusted, and doing the setup, which is getting the convergence and everything set correctly, which is nice because a lot of service manuals skip over a lot of that stuff. And this one definitely has everything you need to know about doing this. If you have a monitor that's out of convergence, often following instructions that are clearly written like these are is probably good enough to work for your color monitor. I wouldn't do it on like a VGA monitor, or at least a high resolution modern one. But if something is old, like a TV set or a CGA monitor, these instructions are almost certainly good enough. And down here on page 33, we actually have the full schematics for the entire set. It's not very complicated. I mean, there are a lot of stages here to the cathode drive, which is what generates your video image. But generally, the TTL signals come in here and they go through some buffers and inverters. They make their way right to the cathode drive stages and the brightness control. And that's pretty much it. Everything down here is going to have to do with vertical and horizontal control. And I think the shaded areas here are either safety critical components like the X-ray protection stuff or high voltage, like this is a switch mode power supply. You do not want to touch anything over here while the set is operating. One observation I have about these schematics and then, well, the whole service manual is absolutely this came from Mitsubishi, who made this monitor. This is not typical Radio Shack stuff here. And I've seen other Mitsubishi service manuals and they look exactly like this. The 1984 Radio Shack computer catalog does talk about the ultra high performance MS-DOS system that is the Tandy 2000. Specifically calling out its 640 by 400 resolution graphics with only 8 colors, doesn't use the intensity bit. Comparing that to its contemporary IBM PC, this machine was only slightly more expensive, but yes, it used the 8186 processor from Intel, which is what led to its lack of full PC compatibility. Now, if you purchased your Tandy 2000 back in 1984, it was either $2,750 for 2 floppy drives and 128K of RAM, or $4,250 with 1 disk drive and a 10 meg hard drive and double the RAM at 256K. Now that did not include the monitor, so you could choose your display, and the CM-1 cost a whopping $799. If you're wondering why this monitor is called the CM-1 or Computer Monitor 1 and it's paired with the Tandy 2000, what about the Tandy 1000 monitors? Why are those called CM4 and 5 and higher numbers? While the Tandy 1000 with its matching monitors with CM dash numbers higher than 1, this came out in 1985. And the CM2 monitor you see here, which has the similar design language to the CM1, this is actually, if I recall, a lower resolution set. Now it does say it's a high resolution monitor and it's more expensive than the CM4, which, well, that looks like a monitor I'm not really familiar with. I wouldn't say this is the Mitsubishi design of these other CM models. And it wasn't until the 1987 catalog that we see the more inexpensive television-derived CM5, which is paired with a Tandy 1000EX here, or the Tandy CM10 paired with the Tandy 1000SX. This is a Mitsubishi-designed CGA standard monitor, but it has the black painted bezel, which matches up to the same styling as the CM1. And they have a little chart here that actually explains all their different monitors. So the CM1 is 640 by 400 text only, or text and graphics, depending on which graphics card you pair to it. And then we have the CM5, which is the low resolution version without the painted bezel. And that's the low cost option here for $299 and 95 cents, just designed using a television CRT for displaying text. And it can do 80 column text, it's just not super sharp. And then we have the CM10 here, which does cost $459, so still $100 less than the CM1, which is kind of ridiculous because honestly, there is no actual difference, if you ask me, with the components inside these monitors. It's just that the CM10 runs at 15 kilohertz and the CM1 runs at 26 kilohertz. But I think the CRT and the rest of the parts in there are the same, so that $100 price difference is kind of outrageous. And I guess the CM2 from 1985 here with the white painted bezel is actually a high-res monitor made by Mitsubishi, but seemed to have been short-lived because it wasn't even in the catalog by 1987. Another little tidbit about this monitor is it does have a little kickstand on it. This little bar here can pop out like so, and it has two possible settings for adjustability. There's this setting right here, which gives a little bit of lift to the monitor, or you pull it down and slide it into the monitor like that, and then that gives you the maximum lift of the front of the monitor. And when you're stowing this little bar, there's a little clip here that it clips into, and that still works. So the funny thing is here is I don't actually have a Tandy 2000 machine, and I've never really thought about the Tandy 2000 because I know it's not really PC compatible. It means you're limited to just the software that mainly came out with it. So then you might be asking, how did I end up with one of the monitors? Well, I was watching VWestlife's video on high resolution video standard that the Tandy line offered, and he had a monochrome Tandy card that actually outputted color, even though it was a monochrome card, and it ran at the same 400 lines of resolution because it was designed to work with a monitor just like this, or the monochrome version of the 400 line monitor that Tandy also sold. And in that video, VWestlife mentioned that there was a seller on Craigslist who was actually selling one of these monitors here in Portland. Well, this is that monitor. I went and grabbed it from the seller, and as I mentioned earlier on, I haven't even tested this. This thing might be totally dead for all I know. So in that case, it was a big waste of money, but rest assured, I did not pay the full asking price for the monitor because it's untested. But if this monitor does have a problem and needs repair, at least it'll make a repair video out of it. And that's why in the last video where I did a repair on the Super Res 400 video card from STB, I actually bought that card off eBay specifically so I could test this monitor because I don't think this thing actually works at CGA resolutions, and there'd really be no way for me to, well, even figure out if this thing worked or not. So before I pull the cover off this, all the usual caveats apply. If you're going to work on a monitor, make sure you know how to do so safely. So in other words, I recommend you don't do it unless you know exactly what you're doing. And let's see if we can get this off. Okay, there we go. And this is where I hate these stupid power cords. You have to feed it through the back cover here, slowly and carefully. Well, right off the bat, I'm noticing that this thing has this glue here. And I hate this glue because it becomes conductive and it absorbs moisture and starts to corrode things. I think I'm gonna need to scratch that away because it's all over the neck board here. And right there, that can cause issues. Well, I noticed there's a little bit of evidence of use. There's some soot and it's a bit crusty, but it's not terrible either. Could be far worse. You'll notice here we have a Mitsubishi color picture tube, 370 MLB22, and 37 centimeters is the size, so very typical size. What we see going on here on the main PCB just seems extremely normal and standard for Japanese imported sets at the time when this was made. I love this little cute warning sticker here that's sort of suspended on these wires. Cut silicone seal between the black socket guide and white socket prior to removing the CRT PCB assembly. Very common on most of these types of things that there is a little bit of silicone to hold this neck board in place. And this is a better view of this absolutely horrible glue that's all over the board here. And I'm gonna definitely need to pick away at all of this, at least on the neck board. And if I see any of this stuff anywhere else on the board, I'm gonna have to do the same. This is what it's talking about here with the silicone. Before trying to remove the neck board, you need to make sure you cut that or you could crack the board. The main reason this is on here is for shipping purposes. So I'm just gonna cut this away. I'm not gonna be shipping this monitor anywhere. It's probably never gonna go into a box ever again for the rest of its life. So I don't think it really matters that that's on there. Now this is the flyback transformer, and there's a little bit of a curiosity here. There's a little flying ground lead from this metal chassis here to the clamp that goes around the flyback transformer. So if you have to remove the flyback, you have to desolder that and make sure to reconnect it. Now that nasty circuit glue that we saw on the neck board often is around the main PCB as well, especially around the large components. It's much more common seemingly on Korean made stuff, Samsung and LG and other things like that, but I don't really see any on the main PCB on this monitor at least. There's actually a set of 4 dip switches down here on the board, and they are off, off, on, on if we start at 1. I checked the service manual, and these are for setting the polarity of the horizontal and vertical sync, and also the intensity bit. I took a look at the controls that are exposed through the back of the case, and you have V-linearity, height, horizontal hold, and vertical hold. The thing is, the horizontal hold control is not a normal potentiometer that you can stick a tool into. It's actually mounted parallel to the PCB. That means you have to put a tool into it this way. And then there is the focus control and the screen control, which are on the flyback transformer. I don't know for sure those are exposed through the back of the case. Oh yes, they actually are. So the top one here is the focus control and the bottom one is the screen control. Now I have the monitor on its side, and unfortunately there's a bunch more of that horrible circuit glue here because there are some components that have been installed here, little resistors and caps and stuff like that. So I'm gonna have to scratch all that away. There's a little bit more over here as well. And one of the reasons why you want to definitely look at the underside of a board like this is you want to check for cracks in the PCB, because if the monitor's been dropped, then it's possible around things like the flyback here that the actual PCB might be cracked, and that can create intermittent faults on the set. And then it goes without saying, of course, that you could have bad solder joints as well, especially around the large components like the flyback, which could also cause intermittent faults. What's good about this design though is the flyback is actually screwed into a metal structure that surrounds the whole PCB. So that usually means it's less likely we're gonna have broken joints on the flyback. But you should really check anything where there's connectors or large components like the flyback and look for any bad solder joints. Initial appearance, everything looks to be in pretty good shape here. You should also try to inspect for any areas where the PCB looks burned, and that happens when the monitor's been running and you have a bad solder joint, because essentially it starts to overheat, and then you'll see visible signs of that. These brown areas here are more likely flux that was just from assembly of the monitor, and the actual joints look pretty good. They're not all crystallized and terrible looking, outside of this disaster that's happening over here. Now, when it comes to removing this circuit glue, I don't know the best technique. And when it gets really dark brown, it becomes very crusty, but this stuff is still somewhat pliable, but it does look kind of scary there. I sort of tilted this up because it was attached to this rubber tube that's around this component, and notice how it's starting to look all dark and brown, and that's when the corrosion really starts to set in. So I'm wondering if I should hit this with some hot air. All right, yes, and the heat gun really seems to help. Now I have this thing set for 100 degrees Celsius, so it's not burning hot. I don't want to melt anything here. Let's just practice on this area down here. So this is really stuck on the board there, so I'm just gonna blast this with 100 degrees Celsius heat, so nothing crazy hot. And after I do this a while, it gets to the point where the whole thing just kind of lifts right off pretty easily. I mean, it's still holding on, but it definitely loosens up. There we go. See, it just sort of all popped off all at once. And now I just want to make sure there's nothing left on the PCB itself. And then as for what's left on this little rubber tube here, let me just heat this up here. I should be able to like pull it off. There we go. That just came off. So I'm just going to work at this and try to get it all off this and off the neck board. And the neck board is the one that looks really bad because it's starting to turn that dark brown, which is when it becomes very destructive and corrosive. Okay, all the circuit glue is off, and luckily nothing was super badly corroded. None of the parts fell off. I did take some pictures ahead of time. So if you're gonna do something like this, take a lot of photos from different angles. That way, if one of these pops off, you can reattach it. In fact, down here on the corner, there was a diode, and this one was actually the worst and the most corroded, and it did come off. So I had to resolder that. But the leads on the package itself are fine. They're just the point where it was attached to the board is where the corrosion was. I did use a little bit of hot glue just to reattach these little boots here so they don't flop around and the components don't flop around. And here's the neck board after I've got all the circuit glue off. It was a bit more difficult here because there was so much of it packed in here. And luckily the components all had these little plastic covers on them, which actually protected them from getting the corrosion from the circuit glue itself. And some of the contacts are a little crusty on the PCB, but I don't think it's anything that's going to cause any issues. You may notice some of this white gunk all over the board here, and this is actually just leftover flux. I was using IPA to help get the stuff off there. Heat and IPA seems to, well, get the circuit glue off the board, but of course it makes the flux kind of accumulate over the lower edge here. I reflowed all these joints though on the CRT neck connector. And I did inspect the top side of the board, and there was actually a little bit of circuit glue between these two caps. So I got that off as well, and put a little hot glue in between them just to hold those up. I also looked over the board here and reflowed any joints that looked like they would be problematic, but I have to admit, I didn't see any bad solder joints, but I still redid the flyback transformer and a couple of the other large components just to be safe. And what we see here is all the leftover junk that I got off the board, the circuit glue and stuff. Some of it probably flew on the floor and other pieces here and there. Unfortunately, the little tag here didn't survive, and these were from cleaning the flux up off the neck board. But yeah, this stuff is insidious and evil, really is. At this point, all I want to do now is remove the high voltage anode cap, and I want to try to just clean around it. There isn't a lot of soot or anything around it. There's a little bit here, so it came up on my finger. But I like to just clean around this area here, just to make sure that we don't have any tracking issues, things like that. I do see some silicone grease on here, obviously installed at the factory. Don't worry, by the way, I've had this monitor for weeks and weeks, and it's never been turned on since I've had it, so it's now fully discharged. So I'm just gonna use a little paper towel here just to clean up around the CRT. A little bit of stuff is coming off, but I don't think a whole lot. When a monitor gets used a lot, there is a lot of high voltage potential around the CRT, and it kind of attracts the dust, a little sort of a black soot. So if you see a lot of that when you open up a set, it kind of tells you that it might have been used a lot. There's obviously a little bit here, it's coming off on the cloth, but not a whole lot. Oh, one thing I forgot to mention, these wedges here. Now these can actually get hard and also hygroscopic, which can corrode the coils because they're touching the coil on the inside. So if they're not soft and pliable, these ones are still, then you might want to pop these off and replace them. The problem is when you do take them off, it can really affect your convergence because the deflection yoke itself can move out of position. Now you might notice this same glue is all around here on the deflection yoke, holding these little magnets on. I'm not particularly worried about that because it's not touching the coils themselves. There's a different kind of glue that holds the coils on, and as far as I'm aware, this glue is okay. And also, if this was bad, there's really nothing you could do because it would be impossible to get off. But I inspected closely the whole yoke, and I don't see any position where this stuff is on top of the actual coils itself. There's a little bit right here as well, but again, I picked at it and it's not touching the coils, which are wrapped around this part of the yoke. I'm sufficiently happy with the amount of cleaning around this area here, so I'm just going to wipe the inside of this and then reattach it. I think there's a little bit of a debate on whether you should have grease there or not. I've seen monitors from factory both ways, and obviously this one had it, but I've had a lot of monitors that did not have it. You want to give that a tug, so make sure that it's on properly, and it is. So lately when I work on monitors, I tend to not put grease on there. But let me know in the comment section if you work on CRTs and you think grease should be applied there or not. I think I'm going to power the monitor up with the board just sort of sitting here on the bench, loose like this. I do need to connect up this, make sure this ground lead is connected, and then put this on the CRT. I'm going to turn the monitor to the side just like so. So when we turn it on, any kind of fireworks, we will be able to see. And of course, the entire time I've been working on this, the power lead has been out of the wall, but I am going to plug that in now. Are we ready for power up, everyone? Here we go. 3, 2, 1. All right, we have high voltage. Now here's the Spectroid app on my phone, which on a normal CGA style monitor, we'd have a peak right around 15 or 16 kilohertz. Of course, this monitor should be running at 26 kilohertz, which I think is really above the microphone capability on my Android phone. It kind of rolls off right around there. So we're really not seeing anything on here, even though I absolutely know that high voltage is working on this monitor right now. And so far, nothing bad has happened. I'm going to power it off real quick. And we hear the static sound as it discharges the CRT. There's a bleed resistor that does that. I'm going to use my high voltage probe here so we can see what kind of high voltage we're getting on this thing. Now, because this has a discharge resistor, there was no charge when I first connected this, but you should never rely on that. And you should always discharge the CRT first if you're ever going to remove the anode cap, for instance. Okay, here we go. Ready for high voltage. Seems kind of low, actually. We're getting about 16 kilovolts. I can't really look straight on because I'm shooting it with the camera, but that does seem a bit low. I'm not going to worry about the high voltage being a bit low, in my opinion, right now. I think it should be around 22, 23 kilovolts. So what I need to do is get something connected to the screen. The power's off now, by the way. I need to get the computer connected to this, and we need to see if we even get an image on this thing, and then I can check this again to see if it's more appropriate when there's sync signals going into this thing. So our first test, successful. Seems to be operating. I didn't see any kind of raster on the screen, but I'm not going to be worried about that. Digital monitors like this don't always display anything when you don't have them connected to a video input source. Some TTL monitors, like IBM monitors, they pull their inputs up to 5 volts where they're not plugged into anything. So therefore, when you turn on like a CGA monitor, you get a full white raster on the screen. This whole screen is just white. When you plug it into the computer, that will go away. Many monitors aren't like that, and they might just show black when they're first turned on. So for test number 2, I need to get this thing plugged into the STB card, and I have a cable here that we can do that with, 9-pin to the EIJ8 connector. So let me get set up. All right, the 36SX board is all ready to go. The STB Super Res 400 card is installed, and of course this was repaired in the last video, so we know that card is working perfectly. We are actually ready for testing. Let's turn the monitor on. We have high voltage, all is good. Power lights on, yep. While it's turned off and I have the cable unplugged, I'm just gonna adjust the controls on the front here, just so you can see that there is no raster whatsoever while there's no video input. Yeah, I'm turning all 3 knobs to their extremes. Nothing's happening. I'm gonna put them all kind of back in the middle here. Plug the cable back into the card, and I am ready to see if this monitor finally works. 3, 2, 1. We have nothing. Oh, there is an image. All right, okay, so the leftmost control is the centering control. That one there is probably a contrast control. And then the one on the far right is a brightness control. Hey, so this does work. That is freaking amazing. It's not very bright. I'll start with that. Let's run check it here. Yeah, that looks quite poor. Yeah, the picture quality is not great, not good at all. Let me just check the connection here on the back. There also appears to be quite a bit of bleeding happening here. Like the red check mark is also very washed out, but it's more intense in this middle part here, and I'm assuming we have some blooming or bleeding going on here. And over here on the side, there is not a lot of clarity for these lines, for instance. Now, one thing you may notice about this image is that the text here, which should be white, actually looks blue. And you might think there's a fault with the video card again. That's not the case though. What's happening here is the blue is bleeding into the white text, and it kind of confirms it by looking at the risers here. They have the blue from the background bleeding into them, but this long white bar here is mostly white without any issues. And the same thing is happening with the red, where the white is sort of bleeding into it, making it look a bit brighter, and the blue is bleeding into it, which makes it all look a little dull. And then looking at this test pattern, yeah, it's just an absolute smeary mess. Now the middle control, as I turn it down, actually lowers the overall brightness of the less intense color, the non-intense colors. These are the intense colors here. And I think overall the brightness control controls the whole image. And that's all the way up there, by the way, and it's not very bright. And adjusting what they call the contrast control doesn't seem to really make the bleeding go away. So I have it adjusted to a point where the overall color balance is a lot better. It's a lot more pleasing. It's still not very bright, and we have this smearing issue. We have a couple issues going on, right? The high voltage seems a bit low, 16 to 18 kilovolts. It's a bit low for a monitor this size, a color monitor this size, that is. And then this smearing issue. Is it a CRT fault, or is this an issue with the circuitry? The geometry on this monitor is working without issue. There is no problem with that. In fact, when we go to here, you can see that the grid lines look really good. There's no issues with geometry. Obviously, I haven't done any kind of adjustments getting this centered or whatnot, so spend a moment to do that, but there we go, it looks pretty good. The issue exists with the cathode drive circuits that take the video signal and convert those into, well, what you see here on screen. But what I am pleased about is A, the video card's working properly, and B, this monitor does work. And I must tell you, the text, even though it's all smeary, is quite sharp. And that's awesome, and I think that's what's so special about this monitor, and why, when this thing was on the market as new with the Tandy 2000, you would have looked at this and thought, wow, that looks great compared to a normal CGA monitor. You don't even see the scan lines. It's just sharp and crisp. Well, it would be if it wasn't so smeary. All right, it is the next day, and well, I've made some progress. I haven't fixed the problem or anything with the smearing, but what I did is I actually installed a potentiometer for the green drive control. Originally that was set to a fixed value using a resistor. So I removed the existing fixed resistor, and then I salvaged this potentiometer off another monitor, and that way I could turn down the green drive, because before I couldn't. All I could do is turn down the red and the blue, but we were always stuck looking at green. And what you could see looking at the screen here, when we're looking at just the red turned up and the other two turned down, is that all the smearing that we were seeing, which I initially was thinking was actually something to do with the blue and the green circuit, has nothing to do with those. It's entirely to do with the red cathode drive. In fact, what I'm doing now is I am turning the green and the blue back up again. And now when you look at the image, there's absolutely no smearing whatsoever. So huge thanks to John in one of the CRT chats that I'm in for pointing that out, that it wasn't the green and blue and was entirely the red, because John was 100% right. It was exactly the red that's causing the problem. And everything now looks super sharp on here when we're not looking at that red gun with all that smearing. Next, I want to talk about the 16 or 17 kilovolts that I was seeing on my probe here. I was chatting with my friend Frank about this problem, and he suggested that I really needed to try another probe, that almost certainly this was a problem with this probe itself. And Frank was dead on right, because I grabbed my other probe here. This one's made by Pomona Electric, and the one in my right hand here is B&K, and the probe in my left hand, when I probe the monitor, guess what? We're getting 22.5 kilovolts. So I didn't realize, but there's actually a little adjustment potentiometer right here on this probe, which basically calibrates the reading, and all I did was just replicate what the other one is. It goes without saying that the way I calibrated this wasn't really calibration, and I need to, I don't know, get some known voltage source that's already calibrated and then calibrate this against that. But the thing is, in talking to Frank, he said that if the voltage was actually as low as I measured it to be, like 17 kilovolts, on a set like this, we wouldn't really be getting much of an image at all. It would be really, really bad looking and almost invisible. So he said that it almost certainly was running at the correct voltage, especially if the B plus was set correctly. And in the service manual, it said the B plus was supposed to be 112 volts. And let's just double check that right here with the meter. So the service manual for this monitor tells you how to check the B plus, but this is a resistor here that connects the power supply to the rest of the monitor. And there's a pin on the right side there, just where the red pointer stick is. That's the B4 test point. And we'll just hook onto that with the probe there. And I have the other probe just connected to the chassis ground right here. And if I turn on the monitor, 112.2 volts. The service manual says it should be 112 plus or minus 1 volt. So I'm going to say that B plus is looking perfect. And in these types of CRT designs, one very much similar to all the CRTs in the 70s and 80s, it's the B plus voltage, which is the primary voltage that comes out of the switching power supply, that really determines how well the monitor works. The 112 volt B plus on this monitor is what basically is switched directly into the flyback transformer, and that gets turned into the high voltage through the windings that are in the transformer. The whole X-ray protection circuit that I talked about earlier has a lot to do with that. If something goes wrong with the power supply and suddenly B plus is running at, say, 130 volts, you have to remember that inside a flyback transformer there are windings on the primary and the secondary side, and it's the ratio of those windings that determine the voltage that comes out of the secondary side, which is the high voltage in this case. So if your B plus is running, say, 10% too high, then one can kind of assume that your high voltage coming out of the flyback is also going to be about 10% higher. And in the case of the 22,000 volts that this runs at, that's an extra 2.2 kilovolts coming out of the flyback. On a monitor like this, the correct B plus voltage is also essential for proper deflection, both horizontal and vertical. So if it was too low, one of the side effects is you typically have less deflection, so the image would just be smaller in the middle of the screen. Not to mention then, of course, you would have lower high voltage, so it would look a lot dimmer. But as we saw here, the B plus is totally fine, so there's really nothing to worry about that. The only problem we really need to focus on with this monitor now is this smearing issue, specifically on the red channel. So I'm going to turn the blue and the green drives all the way down again, so we can be looking just at the red drive. So there's the red starting to appear. That was the bias control. And then this is the drive control. Now, as I alluded to before, we have two possible problems here with this red beam. we could have a problem inside the CRT itself, and that is completely possible. That's causing this smearing effect, and it's also kind of dim, the red. It's not nearly as bright, and you have to drive it a lot harder versus the green and the blue. But we could also be having a problem on the circuitry side that's causing the smearing and also causing this to not drive red all the way. And there's actually a few different ways we can start with the diagnosis of this problem. One thing we could try is just swapping the red and say the green lines that go to the neck board so that we're actually driving the red circuitry on the neck board using the green circuitry on the main PCB. That would tell us right away if we're having issues with the CRT itself or possibly the circuitry that's on the neck board. Another thing we can do is we can use something like an oscilloscope, like this little pocket one here, to actually look at the cathode drive signal that goes into the neck board. The signals that are coming out of the main PCB are driven from a digital TTL signal. That means there's not any analog nature to them. It's just on or off, and there's actually two different brightness levels. That's all we're ever gonna see on this red signal. So if we start seeing all sorts of like smooth things going on, especially like all this stuff right here, that theoretically should be visible in the oscilloscope, and that will tell us if we're dealing with a problem on the main PCB or in the CRT or on the neck board. So because that doesn't involve removing any wires, I think that's what I'm gonna first start with. Okay, to start with, I'm using a 100x probe on this oscilloscope. I like these because it's gonna divide whatever I'm measuring by 100, and that means if I connect to something that's, say, 300 volts on here, this thing is not even getting 30 volts, which it would if I was using a 10x probe, but it's gonna be getting 3 volts. Now we're going to start with connecting the probe to the blue drive signal. So I'm on the actual potentiometer here that it's allowing you to control the drive signals, and I'm on the front side of it. And what you're seeing on the scope there is just a whole bunch of quick moving stuff, but if we hit hold, you can see there's pretty clear ups and downs happening there. And we're at 250 nanoseconds per division, so this is pretty fast right now. And it looks really good, it looks really sharp. And I just moved it over to the green potentiometer, and it looks pretty much exactly the same. I'm just trying to get to a similar spot here. Obviously my ground lead is not perfect, so we're having a little bit of overshoot and stuff like that. But overall, that looks like a pretty sharp change, this up and down. It's kind of what I want to see. Okay, now I connect up to the red potentiometer. It certainly looks different. I'm gonna adjust the potentiometer here. I just want to see, oh, okay, if I turn it all the way down, let's try if we can get, there we go. This looks the same. And you know what? That doesn't look like smearing to me. That just looks like really sharp ups and downs. I'm going to try to find a better place to probe the signal where the potentiometer itself does not affect the signal that we're looking at, because I'm just suspicious that when I turn the signal all the way down, maybe that's sort of masking the problem or something like that. Okay, I took a look at the schematics here, and it says here that the red signal that comes from the main PCB is on pin 3 of the connector. And then that goes into the red drive potentiometer. I was connecting up there. And that was after this divider that was happening here and stuff like that. So now I'm connected right up to pin 3, and this looks about the same as what we were looking at. Let me adjust this potentiometer here. Yeah, there's no longer an effect on the signal here. It looks the same no matter what I do with it. And you know what? I mean, I don't think that that's smearing. That looks pretty sharp. And then theoretically, if I go on the front panel and I adjust the brightness and contrast, see, that does change it. Essentially, we're going to be viewing that there's the intense signal, the not intense signal, and then black. So you should have 3 levels. But if I max out the contrast knob, that's that line there, it moves up and down. So what this tells me here is that the problem we're dealing with is either with the CRT or it's on the neck board itself. It does not exist on the main PCB. So we need to take a deeper dive at the schematics there and try to figure out what components are involved on the neck board that could be causing this issue. This is the red drive part of the neck board, and the signal we were probing before was right here, was actually on pin 3. But the drive signals from the main PCB make their way into this array of transistors here. And then the output is this right here, 95 volts. And that's actually what makes its way through to pin 8 on the CRT connector, and there's the CRT itself. So the problem that we're having is probably in this section right here of the cathode drive, unless it's in the CRT itself. Now notice how there's voltages printed here, 111 volts, 111.8. This is kind of mainly the B+ stuff that's coming in from the main PCB. So I do need to check to make sure that those are okay. But the thing is, like this one right here, 118 volts, this also goes to the cathode drive circuits to the green and the blue. So therefore, we can pretty much assume that that's okay, unless there's like a bad trace or something like that here. And the same goes for this over here. Now what I'm going to do is I'm going to connect the oscilloscope right here to pin 8. That's basically going right into the CRT cathode, so we can see the signal that's coming out of this circuit. Now I know it's flying by very quickly. Now to make heads or tails of this and help you understand this, when the voltage gets down around the ground level, that's fully on. So if you ground the cathode on the CRT, you're actually going to turn it on full maximum emissions, maximum brightness. When you're up here, which is around, I guess, 90 volts, we're at 20 volts per division, that means the cathode is turned off. So these notches you see up here are actually the horizontal blanking happening. This is the scan of the beam going all the way across, and then that's the horizontal blanking section, and then repeat. So this is one line, a blank, as it retraces back to the left side, and it does it again. And then occasionally, if I unhold this, it's hard to see, but occasionally you'll see a line that's just solid across the top, and that's the vertical blanking, which is made up of a whole bunch of horizontal lines as the electron beam goes from the bottom corner back up to the top. Now I presume what we're seeing here is information like text or something like that. But one thing you notice is you see this kind of ramp that's happening here. That doesn't make sense. And what I mean by that is, remember, we're talking about digital signal, so it's either going to be driving it all the way to ground or not. Why is it kind of fading like this, where it's getting closer and closer to the top? That very much looks like smearing to me. And what I'm going to try to do is zoom in a little bit here on this waveform, and I'm going to try to hold it at the exact moment so we can see what I'm talking about. I guess I can try moving this as well. This shouldn't be happening. It should be driving it down to ground, back up here, ground, back up here. Not this sort of fadey stuff happening. This has got to be the smear. It's absolutely got to be the smear. So that tells us that there is definitely some kind of a problem in this circuit. So I think what I should start doing is I should start going backwards on all these components here, and to start to see where that waveform that looks so screwed up on the oscilloscope starts to look correct. Because I know that over here, where this drive control was, when we were probing on pin 3, it looked fine. So the problem does exist in this circuit somewhere, and it's just a matter of figuring out where. All right, I have a couple clip leads connected up here because what I decided to do is swap the red and the blue cathode drives around into the CRT. And this is going to rule out that we have a problem specifically with the CRT itself, which still theoretically could be the issue because it could be pulling down the drive circuit. And what I did is I lifted this resistor here, R679, lifted the side that's facing the CRT. I did it for the red, and down here R681 on the blue side. And then I used clip leads to clip onto the leg that was now hanging on the top side of the board. And then I actually clipped it right onto the connector that's going to the CRT. So what this should do when we turn this back on is we should now have that smeary effect on the blue channel. All right, let's turn this on. Strangely enough, we're not seeing anything now. Turn this back on. Oh, there we go. I don't know, that was weird. Okay, so I have everything turned down. Now if I turn up the red drive and the red cut, we should have it show up on blue, and we do. Okay, well, it's hard to see right now because we aren't on the test pattern. I need to turn up one of the other drives here so I can start to read the text. There we go. And there we go. The smearing is on the blue channel. Excellent. This tells us 100% without a doubt that we are dealing with a problem in the circuitry, and the CRT itself is fine. Awesome. That is quite the relief. So I've restored the cathode drive back the way it was. Red is red, blue is blue, no more clip leads. So I started looking around with the oscilloscope where the signal was bad. We know it was bad coming through this resistor right here. That's the cathode drive. And I saw it bad over here on the base to these two transistors as well. So that implies it's something over here. And then I saw it bad right here on the collector of that resistor right there, Q651. So what I went ahead and did is I swapped this one here, which I think is for green or blue or something like that, and the one for the red, which was over here. Now there was this extra little, I don't know, resistor and diode connected to one of the legs of the transistor over here, and I disconnected that, and that was not what was causing the issue. The issue still existed with this disconnected. This little mod here is not on any of the other transistors on the board. These mods though here are the same on all the channels. So we have a small disc capacitor and a resistor, the disc and a resistor, and there's the disc and the resistor right there. But there was a few other mods that are here and there, including this one here, which was the resistor and the diode tied together. I took a picture of the way that looks, and I'll put it back once I'm done. I'm assuming that just fixes some subtle issue that they figured out at some point. Anyhow, the two transistors are swapped around now, so I just want to see when I turn it back on if the red is still all smeary. Because if it is, then it's not the transistor itself, it's something else in that little circuit right there. We're getting down to just a couple components that are possible for the culprit. And before I turn this on, I just want to double check that those transistors are exactly the same part. 2SC2688, 2SC2688, yes, okay. All three channels have the exact same part there. I didn't want to cause a problem when I turn this on. Okay, so the issue is not that transistor. Cool. And of course, this is not blue anymore. It's red because I swapped those back. So time to keep looking. All right, you may notice that some of these components here are lifted off the board. So I have this little thing here, and there was a bypass cap that was originally installed in there, and I have that off the board, and I have this resistor just sort of hanging out. These are the extra mods that were installed on the neck board. And the reason why those are off is because I wanted to remove the transistors and check them on my transistor tester. So there were three small transistors in play, these three right here, that I thought could be at issue because, well, I already swapped this one with the one from the blue channel. That didn't make a difference. So I thought maybe these were the issues. There's also a little diode down there, but I checked that with my multimeter and it was totally fine. You always want to check for shorted diodes. So I thought, oh, maybe these are the problem. So I removed them one by one from the board. I didn't want to take more than one out because they're all different. So I took one at a time out, tested, it was fine. Next one tested fine, next one tested fine. So far I really hadn't found anything wrong. And what I did is I put the neck board back on the CRT, but I didn't reconnect these extra components here. So this resistor, this little diode resistor combo, and this little disc capacitor here, which was installed between these two legs right here in the middle, just like it is down here. This is one of the other channels, and it's got the same disc capacitor in there. And so does it up here. It's installed on all three channels. So I didn't put those back in, and let me plug this back into the CRT, and let's turn it on. So none of those little aftermarket mods are connected up. And as this thing warms up, would you look at that? No more freaking smearing at all. So it actually kind of seems like one of the mods that's on the board here was causing the issue. I don't know. So what I'm going to do is I'm going to reinstall them one by one and then test and see if it comes back. So the first one I'll do is I'll add this little combo back onto the base of Q651. And there's the monitor powered up. No issues whatsoever. I didn't think there would be because I already had that off, I think after I swapped Q651 with the other one, and it was still messed up. Okay, now I installed the little disc capacitor back in between the two pins of the two transistors. And would you look at that? There's the freaking problem. You gotta be kidding me. That disc capacitor must be shorted. I cannot see any other reason why it would be doing this. I went ahead and connected this resistor right here. I know you probably can't see what I just did. Obviously it worked without it, but it goes to the emitter on Q657. Now the little disc capacitor is a 102K, and putting it in the component tester just says damaged part. So it's not shorted. I don't know what's going on with this little part here. Now if my Googling is correct, 102K is 1,000 picofarads. And I suppose what we should do is turn this back on real quick just to make sure that it still looks good now that I hooked that resistor back up. Actually, I'm gonna say that there is still some smearing going on, actually. Yeah, there is still some smearing going on. I'm gonna remove that resistor because I don't think I saw it a second ago. And I'm gonna see if it goes away. All right, I just removed the resistor. That smearing is gone. So I don't understand how the mod that they installed actually ruined this monitor. Okay, well, I noticed that while we don't have any more smearing anymore, there still is a little bit of like a shadow going on between the transition from blue to red. And I'm wondering if the mods there have something to kind of do with that. Interesting. Don't worry about the fact that the color balance probably looks like it's way off right now. It's just because I haven't done the setup on this monitor right now and I've been fiddling with those controls. But yeah, 100% the smearing is gone, but the red drive just seems a little slow to respond. And I'm wondering if those mods that they had installed help it respond a little bit more quickly to improve the response time of the cathode drive. And now the mod's not applied to the red gun, the other ones are definitely, working fast, and now red is a little bit slow. What I have here are clip leads with that disc capacitor, and I have it across one of the other transistor pairs. I still have the one that was already installed by the factory, plus this one. And I'm curious if we see that smearing now on whichever one I clipped onto. I don't know which one it is. We don't. What? Now I just moved it back to the red transistors. Let's see if we have the smearing now. We do. I don't get it. I don't get it. Watch, if I disconnect this, smearing is gone. Connect it, smearing is there. Okay, I removed the disc capacitor from one of the other channels and I clipped on the one from the red channel that seems to be causing issues. And I just want to see what happens. I mean, there's no effect. Oops, well, the clip lead just fell off, but it was connected. And now I connected the disc capacitor from the channel that was working and I put it on the red channel, and there's a missing disc capacitor on the other channel. And do we have smears? We do. Okay, so there's nothing wrong with the actual capacitor. There's still something going on with that circuit for the red channel. Okay, so I have the mods not connected to the red channel, but they're back on the other channel. And with the red turned down, these other channels are working great. No smearing, nice and sharp. And turning the red back up, without a doubt, it's not like it's smeared anymore, but it's laggy. And that does create a bit of a ghosting and a bit of a smearing. And it's still on the red channel. That's just from the softness that the red is still exhibiting versus the other channels. So we're not fixed. But at least, I don't know what's wrong yet. But at least it looks better now. We know the CRT here is not bad. This monitor has definitely been kicking my butt. I'm on day 3 trying to repair this thing. And what you're witnessing here is my inexperience with analog electronics. The cathode drive that's on the neck board here is completely just analog magic. And when you're dealing with analog circuits, especially ones that you can visually see on the front of the CRT, there's a lot of engineering that goes on to designing the perfect circuit to drive those cathodes as responsively and without any overshoot and ripple and things like that as possible. You're obviously going to be visually seeing those signals that are being amplified through the circuitry that's on here. So any kind of issues that creep up are going to be very obvious and very visible. Now, I chatted with Frank last night after I was done with filming, and I wanted to validate that the resistor and the capacitor that was installed across those transistors was there indeed to speed up the response time. And he confirmed 100% that's what they're doing. And that's why when I remove them, the red channel starts to work properly, but then it seems to kind of be delayed. And I see a little bit of lagging behind on the red channel. And when I reinstall those, we get the smearing problem again. And in my mind, after thinking about this, after sleeping on it, it's almost like a power supply problem. The push-pull transistors, which are the final stage on the cathode drive there, they seem to struggle whenever there's a lot of transitions and we have the high speed or speed up parts installed on the board. And when we saw on the oscilloscope that kind of ramp that was going on, it was almost like it was really struggling to pull the cathode down to ground, which it needs to do to turn it on full brightness. And that ramping kind of screams of maybe a bad trace, maybe due to corrosion. Maybe that's presenting a high impedance ground to that circuit. So as it tries to pull down to ground, it loses the ability to do so. And then that kind of creates that smearing effect. I'm not 100% sure. I can't quite wrap my head around it. So the problem must lie with one of the components before the CRT and after that first transistor. So we have those 3 transistors, we have a diode, there's some passives like resistors and stuff like that. We have traces on the board itself, and I think there are a couple electrolytic capacitors as well. Now, luckily, the design of the red channel is identical to the other 2 channels. So I can start swapping parts between the 2 channels, and we can see which part I swap seems to fix the issue. And of course, I need to do this with those high-speed bodges installed. So that's the extra little disc capacitor here and that resistor, because we need that quick transition time to really exacerbate the problem and show it. So I think from a troubleshooting perspective, what I'm going to do first before I start swapping all the parts is I'm going to fire up the monitor again and put the test pattern up. And then I'm going to look on the oscilloscope at those voltage rails, like the B+ rail that goes into the push-pull transistors on the final stage there. And I'm going to look at that not with multimeter mode, but in oscilloscope mode, because I want to look for any kind of sags in the drive. And of course, I can compare that to the other channels as well, just to see what it should look like. And if I find anything out of the ordinary, I'll report back, and then we can decide what to do. Okay, I might have found something that's potentially an issue. So this is the red channel up here. Q654 is the part of the push-pull that's on the top on the schematic. This one is connected to B+. On this lead right here where this capacitor is, and on the the scope, you can see that it looks like we're up at B+. I don't know, 120 volts. That's correct. And then the bottom one here, 657, the bottom pin where the capacitor is connected, this should be connected to ground through a 100 ohm resistor. And when we look at it, notice how it's kind of moving around a little bit on the oscilloscope. And I don't think that's my probing technique here. Okay, just keep that in mind. Now let's move down here to this other channel here. This is the green channel. Now the transistors are reversed, where it's the bottom one here, where the middle lead that's on the little capacitor there is connected to B+, and there we go, 120 volts. And it's the top lead that's connected to ground. And on the oscilloscope, that's all we're seeing. Well, we're seeing 7.5 volts. It's basically at ground, and that's exactly the same circuit design as the channel up there, where there's a 100 ohm resistor to ground on the top lead. So what's going on here? Well, we're at like 95, 107 volts. That pin on Q657 should be at ground, and it's not. Now that middle pin goes to, I think, here, which is the resistor, and then it goes to over here, which I know you can't see, and that is absolutely just at ground. So either Q657 is leaky, where that resistor, which is 100 ohms to ground, is having to sink some current through 657 here, or maybe there's a bad connection between the middle pin there and this part of the resistor here. But it's very, very suspicious that on this lead here, we should be seeing ground through the 100 ohm resistor like we are on the other channels, and we're absolutely, positively not. Okay, so with the CRT off, I don't see any kind of breaks between the pin, the middle pin here, and the resistor. It's 0.32 right now, but it could be high impedance. But I guess the question is this resistor here, R673, this is the 100 ohm to ground. Oh, is this broken? Wait a second, everyone. Is the resistor R673 okay? It's supposed to be 100 ohms. I'm not getting anything. I'm not getting anything at all. So this is just set for resistor mode here. There it is. But going between the two pins there, nothing. So is this all caused by an open resistor? You gotta be kidding me. Now there was a lot of that glue and stuff there, so maybe we got corrosion. Let's get that out and swap it out. All right, there's that resistor. Looks fine. And been probing it, we're in the mega ohm range. Oh boy. So that was it, it's open. Well, I don't know for sure if that was it, but that was certainly a bad part. All right, so while I'm here, I'm just gonna touch up these little joints I did here for the mods, just to make sure everything is soldered appropriately. And let's reinstall the little speed up resistor mod here. So that goes to the emitter on the lower transistor there. And instead of using these silly tubes, I'm gonna use some of this heat shrink. And with that, I'm hoping that this is fixed because we've actually found our first bad component, and it was a passive resistor. And I thought I went through and checked all the voltages and stuff on here, but clearly I didn't, because if I had done that before, I would have found that that pin on the lower transistor here that should have been at ground would have been floating at 100 whatever volts. And even with a multimeter, I would have seen that. And that should have clued me in that this resistor was bad. Let me flip the monitor around here. Let's see if this has actually fixed our problem. All right, here we go. Ready for power up? And this is still connected to the computer, so we should get an image. And it's just at the check it launch screen. Yes, yes, yes. That's it. That was the problem. Well, I think it was the problem. Let's just get back to our test screen. Yeah, that looks way better, everyone. Way better. Wow, I'll need to do a full setup on the monitor, but I'm really excited here. All the speed up mods have been applied to the back of the board too. So let's turn these up a bit here. Okay, I did a very quick setup there. Yeah, that is the best this monitor has ever looked up until this point. Got the contrast there, turn the brightness up. Oh yeah, nice and sharp. And the red, no smearing. It looks like it's lined up really well. Oh, finally, finally. That was it. That was it. It was this little, tiny, little passive resistor, 100 ohms, died. It doesn't have any corrosion on it. It's not burned. It doesn't look like it should have failed in any way. But 100% it did, because it was causing all that smearing. And just to show you which part I actually replaced, so this is the push-pull transistor on the output stage, and it was this resistor, R673, 100 ohms to ground. That was the problem. When I measured here, where it says it should be at 0 volts, I was seeing it up around 90 or 100 volts. And when I measured on this side of the resistor, we were obviously at ground, so we had a good connection there. That gave us one of two possibilities. Either the transistor there was leaky, and this 90 volts on the base side was leaking through and pulling up this 0 volts through the 100 ohm resistor up to, you know, whatever 90, 100 volts, whatever we were seeing. Or, of course, the resistor itself was bad, but then when I turned the monitor off and checked with the multimeter across the resistor, I wasn't reading anything. And I should have read 100 ohms because it's not in parallel with anything else, and this transistor shouldn't be leaking. And sure enough, we swapped this out, put a new 100 ohm in place, and this is what we have to show for it. Oh, sorry about the line there. The camera's in the wrong mode. A nice, sharp image. So what I need to do now is go through the setup procedure that's in the service manual there to set up the color balance and tracking on this monitor, just to get those controls all dialed in. Although I have to say that the way it looks right now is really quite good. I've done enough of that now that I can do it by eye pretty easily. But ultimately, you need to go into service mode, and there's a switch on the board which puts it into service mode, which just gives you a single line across the CRT there. And then this monitor should be ready to be buttoned up and put through its paces. Well, there it is. The monitor is all back together. It's looking absolutely amazing. And I even found a program, PC Paintbrush, that works with the STB Super Res 400 at a full 16 colors. And doesn't it look nice? Unfortunately, I couldn't find any demo artwork to load here, so I had to make something myself, and I have very, very limited artistic skills. But I really wanted to show off the color capabilities of this card, and the color palette that it actually offers is relatively nice. It's a bit different than CGA in that we're missing the brown color, but you can create a pattern where you mix the yellow and the red together, and you get a decent brown. Of course, it's a pixelated and dithered thing, but still looks pretty good. And the other difference is we have white, gray, and then two black colors. And on regular CGA, you actually have two different grays. The TTL, the analog color decoding happening in the monitor here, could be tweaked theoretically, but obviously I think this is the way it was designed, at least when in use with the NEC PC 9801, which of course is where this video standard came from. In the end, there was just one single faulty part in this monitor, and it was this little resistor here, which I just dropped on the floor. And that was causing all that smearing and horrible looking display. We also have this resistor, which is not damaged. This was just one I had to remove when I installed the green drive potentiometer. And lastly, I have a couple extra little rubber tubes that were on the little mods or bodges on the back of the neck board. I used heat shrink in the end just to cover those up instead of using these, because these are all kind of dark brown and crusty anyways. And it's really nice to see that this monitor and the paired video card are finally working well. There we go, some full screen color action. Maybe I should have drawn these a little bit bigger to take up the entire screen. There we go, I've defaced my artwork. So there we have it. That's the Tandy CM-1 or Color Monitor 1 from 1984. This one now fully works, and it's awesome to see this thing working on the STB Super Res 400, which Tandy also sold, so you could use this monitor with later machines, not just the original ill-fated Tandy 2000. If you have a Tandy CM-1 and it is working, I highly recommend you open it up and check for some of that circuit glue that this thing had, and if there is any, you need to remove that. It's only going to get worse and worse until it starts to absolutely corrode traces and eat components, and then you'll have a non-working CM-1. Finding the circuit glue in this monitor really reminds me that I need to go and open up my IBM PC Junior monitor, which is also Mitsubishi made, and look for circuit glue in there, and also open up my Tandy CM-10, which is a Tandy 1000 CGA type monitor, and look for circuit glue in there. I've never opened up either of those monitors because they've always just worked perfectly, but this is really a good reminder that it's a good idea to always open up monitors and inspect for this glue and remove it if you see it. As far as the repair goes on this monitor, you could tell by the starts and stops and the twists and turns that I was going down that I don't really get analog electronics that well yet. I'm still learning, and every time I do a repair like this, it gives me a little bit more knowledge that I could use for future repairs. I've learned from previous repairs to always check for things like shorted semiconductors, diodes, transistors, and things like that, which I did do on this repair just off camera, and those were all fine. This isn't actually the first time I've done a repair on a monitor and had an open resistor. It's just that that's not really a common fault. It can be if they're burned, or there's corrosion, or there's some sign that there's a problem. But the resistor that had failed on this thing on the top side of the board looked absolutely fantastic. So unless somehow the corrosion from the circuit glue had made its way through the board to the top side and corroded it somehow, not 100% sure. But the real lesson for this troubleshooting exercise was that if I had gone through and checked all the voltages, which were marked on the schematics, and paid proper and close attention to those, then I should have been able to figure out that instead of that pin on the transistor being at ground, it would have been at like 90 volts. And right there, that should have clued me into the general area where the fault was. So I hope you enjoyed this CRT repair video. If you did, I'd appreciate a thumbs up, but if you didn't, you know what to do. I know there are sections of this video that are out of focus, and I'm really sorry about that. I'm just more used to using my bench setup here for doing repair videos, and when I'm using my camera on the tripod here, sometimes it focuses on the wrong thing and I don't notice, even though I have focus peaking turned on with the little display. I ideally need to get a larger HDMI screen to plug into the camera that I can mount on the tripod somehow. So when I am recording these types of repairs, I can see that it's out of focus and I could just manually fix that. But unfortunately, as I get older, my eyes aren't super great close up and I don't always notice on the screen of the camera that it's not in perfect focus. So I do apologize about that. But anyways, thumbs up if you liked it, thumbs down if you didn't. Huge thanks to my supporters. They make it possible I do this full time. You can become a supporter, links in the description below, Patreon, YouTube membership, you know, all the usual stuff. And I have to give a huge thanks to VWestlife for putting a copy of the ad for this monitor in his video that I was able to see so that I could end up with this monitor and make this repair video, which you are watching now. If you haven't seen VWestlife's video yet, or you don't know his channel, of course there's a link in the description below. I highly recommend you check it out. Amazing stuff over there. All right, that's gonna be it. So stay healthy, stay safe, and I'll see you next time. Bye-bye.